start that. So remind me in case in the future I don't start the recording, I will be recording each of those classes that you can recap them and you can go through them again and through the pertinent parts, particularly when it comes to the coding. Good. Okay. So for today, we're going to talk briefly about data sampling and the design of experiments. And these are really slides that do have a little bit of a public health epidemiology touch, but I think it's relevant and a good starting ground essentially for you to find into how to employ methods then in the following. So all of you will go into the realm of artificial intelligence. That means these methods will be utilized by those more advanced analytics, but basically the underlying principles will be the same. So we talked about the course. That's me. I do research in chronic kidney disease. I talked about that. I do mainly big data analytics in terms of predictive modeling, predictive analytics, basically outcomes modeling, repeated events, as well as time to events analyses. These are basically the main foci of the research that I'm doing. That in addition to various other different topics. But we have, at the Institute, we have founded one of the largest dialysis databases of the world, where we have gotten different dialysis provider to contribute their data to. And we basically were looking at analysis in 200,000 to 300,000 patients longitudinally over several years. So this is really kind of my forte and what is really what makes my heart beat faster. Okay, but let's shift gears. Let's go back to where we're gonna go in this class. So basically, the question is here, what is statistics? So firstly and foremost, whenever you hear about statistics, usually they give you two main tasks of statistics. One is descriptive statistics and inferential statistics. The argument here is that there's a third mainstay, main pillar of statistics, which is really the design, the analytic design of projects. So whenever you plan research, whenever you plan a study, you should have a statistician on board to basically help you to design the analytic approach, to also help you in case this is for a clinical study, also to inform you how to obtain the data, how often obtain the data, and how you basically go about data collection. But yeah, so the two classic mainstays that you will find in every statistics summary book is basically the descriptive statistics. So this is the summarization, and to make the data more palatable, that you can basically interpret it and you can display it and interpret it based on their central tendency, which is kind of the middle of the Gauss bell curve, and the variability around that central tendency. And we'll talk about this in the following. Then thirdly, we have the inference, and the inference is really the inferential statistics part. So you make decisions and predictions that account for uncertainty and incomplete information. In the end of the day, you want the statistics and analyses that you've done in your sample, you want to find a way to be able to use this for decision-making on populations. And this leads us, well, to the definitions. So this is a timeline of statistics, basically outlining over the years how statistics has been relevant in our life. And there's actually, those of you that are interested, that's a very nice statistic to basically give an overview of the different milestones in statistics, which contains like really milestones, which are incredible, like Alan Turing's cracking of the Enigma code, that goes then further to the first computers that were basically used that filled whole buildings in essence, and the computing power is like comparable to that what you carry around in your pocket nowadays. So it's really beyond believable where technology has brought us. And nowadays, essentially in the realm of artificial intelligence, it's like you go on an online retailer, you order whatever you mean to have in your hands the next day, the warehouse next door or in your vicinity is right now already stocked because somebody, some algorithm has predicted that you will be purchasing this tomorrow or by the end of the day, and they will need the tomorrow to have this shipped to you. So it's these advanced analytics have really found their ways into our lives and have made our lives much easier, but to some extent also more transparent, one has to say, a little bit easier to predict. But basically, we are looking at trying to gain insights into what happens in populations. And the definition of a population is really up to you for the question at hand. So it can be all people in the world, it can be American adults or residents of New York, but you mean to describe and make inferences on the dynamics in your population based on samples. And these samples are basically subsets of your population. And the reason for those subsets is essentially because it's virtually impossible to study an entire population for logistic, organizational, and cost-related reasons. So you study samples. The only time where you basically would survey an entire population, this is in the times of the census, where basically you have a large majority of a population that is being sampled. And that would basically constitute a characterization of the entire population. But everything is based on insights that you gain from samples. And that's also true with the NHANES. And these samples basically constitute single observations, records, and they are basically collected in a way, and we'll talk about this when we talk about sampling variability, they're collected in a way that this sample is generalizable to a population. What does generalizability mean? And that's essentially, I will use a lot of terms, and this terminology I think is kind of important to facilitate the conversation you may have with various people that you will be working with in the future. And generalizability is a term that is extremely important when it comes to sampling, and that possibility, the transferability of insights that you make in your sample to a population. Generalizability is essentially how reliable does your sample reflect the entire population? And as you can imagine, this is kind of a problematic topic when it comes to research, because most research basically resorts to so-called convenient samples, samples that are easy to collect data from, because for whatever organizational research convenience reasons, it's just the sample that is at your disposition at that point. The problem is this is at the cost of generalizability, where you basically suffer in terms of the transferability of your dynamics to the overall population. Convenient samples essentially, and the lack of generalizability also is problematic when it comes to the estimates of the prevalence of a disease in populations, for example. And that's the example that I keep on bringing up in this context whenever I'm talking about generalizability. Let's assume a population to present with a quote-unquote prevalence, which is basically the proportion of a population suffering from a certain condition, from a certain disease. Let's assume a prevalence of diabetes in the US population or in the New York City population of around 10%. There's a difference if you mean to estimate the prevalence based on a sample. If you sample it, let's say you go out on the street and you sample 100 people here on Lexington Avenue, or you sample 1,000 people from all the 5 different boroughs of New York, or you sample 50 people next to a diabetes clinic, right? So it affects where you sample from, what strategy you use for the sampling, to what extent your data is generalizable to the overall population. So that is sample and population. So a lot of the analysis that we will be doing is essentially an analysis of a sample. So it's a sample statistic, and we will be quantifying the probability of this essentially translating into the dynamics of a population. Okay, any questions on sample or population? Then we can continue. Okay, descriptive statistics. What do you use descriptive statistics for? You basically use them to describe populations. In what context are you describing them? You can use them in different contexts. You can have various different data types that you're characterizing. You can have a population distribution of a certain characteristic of blood pressure, of blood glucose, of various other lab parameters that you could think of glomerular filtration rate in the realm of renal function. You can have a descriptive statistic of such variables. You can also quantify mortality rates, which is essentially a rate. A rate indicates that you essentially have a time during which this event essentially occurs, which is death. So you basically have a death count per year that you then commonly would standardize for a certain fraction of the population. So mortality rate here in the context of this graph. So you have your deaths per 1,000 population as a function of time. So you see, starting with 1800 up until 1955, you see here mortality rates in New York City over time. Mortality rate is here quantified as the number of deaths in one particular year divided by the amount of people living in the city during that time. That gives you the rate. Basically, the unit would be per individual, but basically then per individual year. Then you're multiplying it by 3 per year. Then you're multiplying it by 1,000. That basically gets you to 1,000 population years. So you're standardizing that rate by dividing the count by the denominator, which is the population. You're standardizing it to 1,000 people in the population. So that is the proper unit of a mortality rate. You have a standardized time, person time, essentially. That can be, most commonly you see 100 patient years or person years. That's the most commonly unit for a rate, for the mortality rate. And that is sometimes interpreted a little bit simplistically to a percentage, because you're standardizing it per 100 person years. So it's the percentage of dying, the probability of dying during 1 year, which is, strictly spoken, it's not really an accurate way of expressing it, but you see it quite frequently. So rate should actually then always be per person year. But what you see here, when you look at this graph, you see mortality rate over time. And what's interesting on this is that you can literally use your descriptive statistics to draw inferences about what happened during those times in that population. And you see various entries with various different disease occurrences, and these basically leads to spikes in the mortality rate. And that really illustrates how useful descriptive statistics have always been and will always be to really understand dynamics over time and to really understand the distribution within a population. Next, we also have inferential statistics, and this is basically an approval rating based on multiple polls. So each of these data points basically constitutes one survey that was conducted for the approval of a particular, I don't know, council member, mayor, president, whatnot. And you basically see each of these contributes one data point and one estimate whether a certain fraction of the respondents approve or disapprove of the candidate. And when it comes to these surveys, and we will talk about this in more detail, you always see accompanying the reporting of a survey, you will see a report of the so-called margin of error. And the margin of error essentially is an estimate of the variability of a mean estimate within a certain sample size. So you basically, you have a sample that gives you an estimate of a mean, and you're estimating based on the distribution within that sample, you're estimating what the variability of several surveys of the very same sample size would produce. And based on that, you can essentially create a margin of error, and that basically is a marker of the transferability to your population, because it allows you to quantify the confidence that you have in a certain estimate. And it gives you the so-called confidence interval, which we will calculate at one of the later classes. And this confidence interval, you can basically choose based on the distribution of this estimated variability of your samples, sample mean estimates. You can set at a certain probability at which you want to choose it. So most commonly, and most of you may have heard of the most famous 5% p-value that most research is striving to. So most commonly found is the 95% confidence interval, whereas you can also make it more stringent with 99% confidence interval or 90% confidence interval, but you basically can set this customary confidence at every probability you want to set it to, and you can basically use the statistical tools to quantify that confidence. But basically, this is the transferability of your sample estimate to a population estimate. So when you hear something being reported with a 95% confidence interval, this is literally meaning that this is an interval within which you're 95% certain that it will capture your true population mean. So that is essentially the confidence interval, which allows for you to basically translate your sample estimates to a true population mean. And that's where you basically move already into the realm of inferential statistics. And that we will be doing with hypothesis testing in the following, at least starting with class 3. Good. Descriptive statistics, inferential statistics. Any questions on this so far? Good. So those were just the simple terms that we are on the same page. So that's quantifying the uncertainty. Now we're briefly going to talk about data, and I assume most of you have in some shape or form learned in previous classes and previous education about the different types of data. So you're basically looking at nominal data, ordinal data, discrete data, and continuous data. Nominal data can essentially be binary or dichotomous, or it can be categorically. And that essentially can be a control versus a treatment. And that becomes important when it comes to analysis of randomized controlled trials, for example. We'll get into that. It can be dead or alive. If you have a certain period during which you are monitoring a certain group of people and you want to classify them of whether they survived this follow-up period or this observation period or they died, you would categorize them in a binary fashion in either alive or dead at the end of your follow-up period. It can be nominal data can also be categorically, so that can be the blood types. And these can interchangeably either be a numerical value or it can be a letter. So this is really not changing the nature of the data type. So they are nominally numbers, so to say, but they are basically nominal data. Ordinal data is basically data that is ordered in some shape or form. Classic example here is the performance scale. So it's either fully active, can do light work, can do no work, or is ambulatory for more than 50% of time, ambulatory less than 50% of time, or is disabled. Again, the number is here ordinal, but basically the concept of what is written next to it is also ordinal. So essentially, it's an ordinal data type. The order is really here important. The magnitude is unimportant. Rank data, okay. So when you have here the number of deaths for leading causes of death in 2010, and you look at these various number of stairs, these are essentially the order here is important. The number is giving you the order, but essentially the number per se as a magnitude of that number does not really matter. Only the order matters. Where the number is now important is when you look at these counts of the number of stairs, because this is when the magnitude matters. So this is when the very same data essentially is being utilized as the magnitude of that actual count, and that is basically treated as a discrete number, which has analytically different ramifications and would be looked at differently, because that you can actually analyze. The numbers you can actually analyze. Good. So here you have again the standardization. So that's again that's a death rate. So you have again the standardized death rate here, standardized per 100,000 of the population. Also, what's interesting here, you have an age-adjusted death rate. Age-adjusted is kind of an interesting thing. We're not going to go over how to do that, but essentially age-adjusted takes into account local cluster of age distributions. So essentially when you compare, let's say Florida, which has a different age parameter than, for example, New York City, and you want to compare mortality rates for a certain condition, you need to have an age-adjusted death rate because of the differences in age distribution. Because if you have a larger proportion of elderly people or people at a more advanced age, I shall say, you obviously have a higher risk of a certain disease as the outcome. So you're more likely to have cardiovascular disease when you are at an advanced age as compared to a younger population. If you compare now a state or a region where you have a larger proportion of people of advanced age, and you want to compare this with the rates in a region where you have a younger population, you need to adjust these for age. And that is basically done by the distribution of age within that population, that local population. Just as a quick side note on this graph, but basically this is discrete data. It basically gives you counts, and these counts are here essentially standardized per fraction in the population or per the counts of members of the population, and that's how you standardize it. But it's basically both counted as discrete data. Okay, magnitude matters, arithmetic applies here. And lastly, continuous data. And continuous data is really the most common data to some extent, I would say. Traditionally, everything that is being measured in some shape or form, everything that pertains time, weight of a study population, length of or height, I should say, when it comes to study population, height, or the weight, mass of individuals in your study population, that will traditionally result in continuous data at your disposition. These data can be bounded or unbounded, meaning they have physiological limits that are just given by the nature of that variable. So if you, for example, if you have a heart rate that is not possible and not to be seen as viable, you would see this as a natural bound to that data, logically. If you have a body mass index or a weight that is just not to be possible and not viable, you would see this as a natural bound. And all values, the interesting aspect here is that all values are possible within those bounds, with whatever granularity, whatever accuracy you can actually measure it with tools at your hands. What is to be kept in mind, and we will talk about this briefly, is like the accuracy of a measurement is always somewhat that needs to be understood in much detail, because believe it or not, you will find a lot of variation and variability between the most accurate measures. And there's really not many measures that you will see as being 100% accurate and repeatable and give you the same result over time. So that measurement accuracy and precision always needs to be kept in mind when it comes to collected and measured data. But again, magnitude matters and arithmetic applies. Summarization of data, and again, there will be a lot of recap probably for most of you. It's extremely important because all the data that you're collecting, particularly when you look at large data sets, as you can imagine, if you have data of 100,000 patients, the way you're summarizing your data does indeed make a lot of, or has a lot of importance, because only if you summarize it right, it will actually be able to provide insights to you when reviewing it. And I cannot overemphasize the importance to always look at the distribution of your data before you start any analysis, before you do any computations on that data, because you need to understand exactly what your data looks like before you launch any advanced analytics on it. Please make sure to always understand your data in much detail. We will talk about this, and I will probably sound like a record was a scratch at the end of this class, because we'll say that quite often. Okay, so you basically distinguish between a numeric summary and a graphical summary. You can do this for all of these data types. Please do not use pie charts. So every statistician will basically tell you to never use a pie chart because it's a very little to non-informative graph because it gives you some overview, it gives you some graphical depiction, but it really doesn't give you more than a percentage. It doesn't give you more than an overview that could be given with much more value using a bar chart, essentially. Okay, that's just on a humoristic note. Yeah, so also understand that the pie chart, that you know how to interpret the pie chart correctly. Numerically, summarization, basically you need to understand the frequency tables, and there you really have contingency tables as a very, how should I say, important way to depict discrete data. So basically it provides the total number of each variable, and it gives you each entry, how often that occurs. Particularly when it comes to categorical data, contingency tables are really the most elegant way to depict this data. As a way of how you can actually look at this, so you have a clinical trial, you will have treatment and control, you will have those in a one-to-one fashion, you will have half in the control group, half in the treatment group. If you have the severity of a disease quantified on a scale from let's say it's a scale from 0 to 100, and you have stratified this in 3 different groups. You have 20 respondents of your 100 respondents that they have mild pain, let's say. 30 said they have moderate pain, and 50 have severe pain. You can now utilize a contingency table to basically aggregate this in a way that you can analyze that. So the contingency table, basically you have to look at columns and rows. And this being said, these marginal totals, which are basically these totals here on the outside, are basically adding up to 50 in both groups. And they add up to 20, 30, and 50, which is the severity that we've seen on previously. So these marginal totals are basically now spread out over these joint groupings. And that's important because when we talk about the chi-square, which is a non-parametric test that we'll do in class 10, I believe, we will basically learn how to analyze for associations in a situation like that, in a contingency table like that, which basically gives you an idea of whether there is any association between the treatment assignment and the actual severity of pain. So it's just really a very valuable way to depict this data and to look at this data in a tabular format. So you have those marginal totals, And marginal totals then also allow for you to quantify marginal probabilities. So you have 0.2, 0.3, and 0.5 for the pain severity, and 0.5 obviously for treatment and control. So all of this is very logical, but all of these things will come back in different shapes or form. And I just want to make sure that these terms have been discussed at one point. Good. So you can set pie chart, rather use bar charts if that's a way how to build those bar charts. You can also show them in stacked bar charts like here. There's another way to depict this data. You can have frequency tables. You have with frequency tables, you need to select appropriate bins to actually discretize your data. That means if your pain severity is a reported continuous variable, and you can have any value from, let's say, 0 to 100, if you are discretizing those as per the severity of pain, you count the actual entries within that bin that you have defined. So that's how you can essentially then stratify that. So let's say you have a pain scale from 0 to 100, and you're trying to discretize that. You can either do this population-based, and you can kind of assign them in 3 different groupings that you kind of split the population in 3 equal parts, or you do them based on previous studies or previous definitions that have been published in that respect. And so here you would have mild from 0 to 30, you have moderate from 30 to 50, and you have severe from 50 to 100. So the discrete numbers then, the actual counts within the respective categories then changes according to your stratification and your bin definition. Smaller bins is a bigger table, yeah. So you can literally show this, of course, with much more granularity, and you can drill this down to different bin sizes. Why is that all important? Because you can also look at such a distribution of the number of entries in the form of a histogram. Why is a histogram such a useful way? Because it also gives you the shape of this distribution, right? And we all know the Gauss bell curve, and we all know how that looks like, and the beauty of its symmetry and the way you can actually look at this bell curve and how you can make as the basis of parametric statistics, how you can actually use this for inferential statistics, as we will do in the following. But a histogram is really the way how you would need to start thinking about data and the distribution, the frequency distribution of your data. And classically, you have the frequency on the y-axis, and you have the magnitude of the assessment on the x-axis. And this is really, this plot should be the first thing you compute before you run any statistics on any variable. Make sure to always do histograms and understand the distribution of your data. I cannot emphasize it enough. So now when it comes to the bin size, so we talked about the selection of the bin size. So now compare this graph to the previous graph. So now you all of a sudden you have selected bins of increments of 5, rather than having the individual entries, right? We have increments of 2. So obviously this looks entirely different, and you lose a lot of information. So you lose this granularity. Estimates from Doug Altman in a publication he put forward was that you lose a fifth of information of your data essentially, and that's more an estimate than anything. But he discouraged from discretizing and to choosing too large of bins, because the categorization per se makes you lose a lot of information. And Doug Altman was is a brilliant statistician who wrote a lot of groundbreaking papers. So it's very interesting to listen, to read his opinions on categorization. So it's always good to look at raw data first. And whenever you start categorizing, be very cautious about how you increase your bin sizes, because you lose information and you lose a lot of insights in your analytics. It is a subjective choice, but it needs to be done very carefully. Good. So here you have now these groupings that we have discussed before. You see now mild, moderate, and severe. So that's a population-based stratification. And you see here the actual entries of responses in terms of this pain severity scale. What you can also do, you can basically fit a function through these maxima of the respective pins. That's how you basically can construct so-called frequency polygons that basically, this one is basically not very smooth, but you usually see them very smoothed out over the entire range of your data. And these are called frequency polygons. And if you're smooth, then with a probability density, you get much smoother frequency polygons. Frequency polygons then leads us also now to another way of looking at data, which is the so-called box plot. And the box plot is a very elegant way to essentially show data. I will talk about these visual displays a little bit more in detail in one of the following classes. But basically, you have with the box plot, you have that middle line basically gives you a split half of the entire population in two equal parts, greater and smaller than that part, the so-called median. And then you have within that box, you have 50% of all your data in the middle part. So you get the middle 50%. And then you have the whiskers, that's basically the IQR multiplied by 1.5. Plus the outer limits of the box plot, but we'll talk about this more in detail. But basically, the box plot is a nice way to show you this central tendency and shows you the entire range of your data, and also indicates the outliers that are basically indicated here, which essentially you all want to understand, because these outliers are basically sometimes really, what should I say, making your life a little bit harder as an analyst. Good. Any questions on any of this? If not, then we can go on. So percentile is the percent of data below a given value. Also important, yeah, that's a good one. So we have this 50%, splitting 50%, splitting your data in 50%. So basically that means 50% of your data is below the so-called median. The continuation of the thought is to talk about the so-called percentile. And the percentile essentially is that number on the x-axis where you have a certain specific percentage of your population below that number. So essentially each of these points constitutes a certain percentile up until that point where it's maximum, where the maximum entry is, that's the 100th percentile. So 100% of all the data is below that point, or the zeros, well, the zeros percentile, which is the minimum where there's nothing below. So essentially, then you go from 0 to 100, and you basically categorize your data based on these percentiles. And this is actually a very important insight when it comes to population insights. Thinking of the medical realm for a second, in pediatrics, where basically you quantify the height and the weight of children, you actually, you don't really know what's the right weight for that kid at any point of time. So you basically, you use population estimates, and you're saying that kid that is in front of me is now conformed with a certain percentile within that overall population. So basically, you are ranking the child at each step of their development according to percentiles that are basically quantifying that child in reference to the overall population at that age. So that's how you basically use percentiles in real life. Good, percentiles. Then we have the quartile. Those are 25th, 50th, and 75th percentile. That's Q1, Q2, Q3. We will split data in quartiles, and we'll get to that later. But it's basically, it's 25% is less than Q1, 50% is less than Q2, is consistent with the median, and 75% are less than Q3 under the 75th percentile. Good. the IQI is from 25th to 75th percentile. If the data is not normally distributed, it's actually the nicest way to depict this data as a median and a 25th, 75th percentile rather than a mean plus minus the standard deviation as you would report normally distributed data. Well, we'll get to that. Good, but this is basically quantifying the population and where the respective parts of your population basically distribute into, and these markers just give you a good estimate of where all your data is basically occurring most often in a way. Yeah, the whiskers is Q3 plus 1.5 IQR, and you have outliers. Good. Any questions on box plot? I highly recommend this as being a very useful way of depicting data and depicting and comparing groupings, essentially, because you have this distribution depicted in your graph. Good. Another way of depicting data is here a so-called strip chart. So you have here the occurrence of each entry depicted here as a strip, and you see those areas where it's a little bit more dense, where you have an occurrence of more responses. So you basically, based on that, you can also find insights in the distribution of your data. And then you can combine it all, and that's a plot from SAS that basically contains then every analysis that we just discussed basically on one graph. I say it's a matter of taste. I basically find this a little bit too overly packed, but again, it's an individual question. But I would not submit a graph like that to a journal. So I think sometimes you want to maximize the information in there, but you want to do it in a way that gives you a very good overview. Whereas this, just analyzing and interpreting this graph can keep you busy as a slide for the next 10 minutes. So it's kind of sometimes less is more, but you got to be very specific on what you want to show. Good, but basically many of the statistical softwares give you full packages where you can pack a lot of information in just one graph. Maybe not always the best approach, but again, that's dependent on the use case for which you're computing that graph. Summarization. Good. Any questions on graphings? We'll talk again about graphs in a bit more detail. Now we can finalize on nominal ordinal data. We have frequency tables, histograms, box plot, frequency polygons, scatter plot, and strip chart, and that brings us to the end. Any questions on this? If not, then we can do a little bit of R coding for today, just to get started. So you do have on Canvas today practice lab number 1. So keep in mind, these practice labs actually do have points values. So you're actually asked to submit those within a period of time that is given on Canvas. And this is supposed to be within a due date of a week. So by next week, I'm expecting a practice lab to be sent and submitted, which will be subject of grading. So we have here data. So we have 2 data files today, and Dr. Arbuthnot. And this is just really to kind of gather. Svani entered the waiting room. Hello? Okay. So these are 2 data files, and this is just to have some data that we can kind of start to do some analysis on, some descriptive statistics, and to kind of get started in R. So that's basically a file from Dr. Arbuthnot. Dr. Arbuthnot was a physician in the UK in the 17th century, and he basically went through the birth registries of his times, and he quantified the records of girls and boys. And so he did analysis, and he was wondering what changes the ratio between boys and girls born to a population. And while that is not a research topic we will pursue in much detail, I thought it would be a good fun first start to kind of reproduce his graphs and do this for the time from the 17th century. And then we have the present data file that basically is CDC data that gives you an overview over the late 20th century. So I thought of this being a nice first start in some coding. So I hope all of you have R and RStudio installed. Just a little bit of background. So some of you may be quite comfortable with R already. For those that are not, please follow along with these more simple explanations of R. Those that are super familiar with R, is a recap for you. So you have R. What is R? R is an open source statistical software. Open source means that it's currently still subject of development. You can go back to the source code of the software of every package. You can basically go and alter it yourself. You can essentially develop your own packages. You can develop your own functions. You have a lot of freedom of what you actually want to do in R. You actually will find on a platform, I don't know to what extent you are familiar with GitHub, you will find coders, statisticians publish their own packages on GitHub, free for you to use and download, and to essentially use for your purposes. So you essentially can do a lot of things yourself, but that's basically R. And R has really, it has now quite some history. It's a collaborative project, which the University of Vienna was involved, various contributors from the US, from Switzerland, from the UK, that basically shaped and formed R as a software. It's open source, it's free, and it basically allows for the use of compilers like here, that is RStudio. That's pretty much the most popular one. You can use R and RStudio by either downloading it and installing it on your local device, or you can alternatively also go on POSITX and use it online in a little platform, which is literally allowing you to do this in a so-called cloud. Hypothetically, you can also do it there. You don't need to install it on your own device. You can also do it on the cloud. I don't encourage or discourage from using either approach. It's essentially both will allow for you to do the exercises we're doing here, or will allow for you to do the analysis that are needed for this class. What we will be using are here two source codes. Okay, now let's stay with R. Okay, so RStudio then. So R is really the left lower quadrant. That's R. The rest is RStudio. So you have on the left upper quadrant, you have the so-called script. The so-called script, if you open RStudio, you will only have this mask. Only if you open your own script, you will essentially have a left upper quadrant. So that's a script. The script here is nothing else but a text file where you enter code. And that you can open this with a text editor. It's literally nothing else but a text file. And you can code whatever you want to code in here. You have here mask for RStudio, which is kind of consistent with whatever you would use with another application. It gives you with the recent files, you can always open up the recent files. Good, that's the left upper quadrant. The scripts are here organized in tabs, just like you would use it with every other file. You have here, and I'm only going on the tabs that are here by default. We can talk about the details another time. you basically have the right upper quadrant. That's your so-called environment. The environment is pretty much, that's like your working memory in a way. So everything you load will end up in the environment. So if you develop any form of object, which is nothing else but a data file, it could be a spreadsheet, you could import a spreadsheet, or you can write your own little data files. Swami, hello? There are like 5 people on Zoom already. Okay. So you can essentially develop your own files. So you can do a little vector, and you can just briefly develop this vector. So I'm programming now in the actual R. This is on the left lower quadrant. And you will, on the very left, you define the object that you want to define. You have then with a smaller sign and a hyphen, which is the R equal sign, so to say, you can in the following define what you want in that object. So if you say, okay, so I want my VEC, my vector. Vector is basically a list of numbers. If I want that vector to look like with C, you basically indicate that there's a concatenation happening. You want several numbers listed in one vector. You say C parentheses 1 to 10. It basically will create a list of numbers from 1 to 10. Simple, right? You can also do 1 to 10 and 20 to 30. We'll basically create the same thing. We'll create 1 to 10 and then 20 to 30. So you basically can concatenate. You can concatenate various bits and pieces, and you can add whatever you want to add. With the cursor up, you're basically going back to the previous code that you typed, and you can go back to all of these codes. You can also concatenate then. Those my initials. You can also add something non-numeric. But now, what happened? If you look at that, and this is, I want to emphasize that already at this point, because your data matters, and you understanding what your data contains matters as well. So if you look right now at the characterization, you have 1 to 21, and you have INT, stands for integer. Why does that matter? Because if I do 1 to 10, 20 to 30, and my initials, then all of a sudden I have here a character entry. And it doesn't really care. It will enter that character. But now look for the characterization of whatever you have now entered that renders your entire vector as a character vector now. And I just really, along the lines of what I said earlier, always make sure to understand your data. That also pertains the type of your data. Understand what R is making out of your data. And you will see that when you upload the data files that I've provided for the final project and other data files that we will see in the following, you sometimes will need to transform variables because R is not perfect when it comes to importing data. So always make sure that you go and you characterize all the data frames that you imported. I cannot emphasize this enough because a lot of errors can happen and you may not notice them. So really make sure that you do a diligent job on reviewing whatever you imported. There is a function called str that will basically allow for you to characterize all the data frames, all the variables in the data frame. With str, you basically get an overview of what type your variables are in your data frame. Make sure that you do that with all your variables. You can also do a summary, but we get to that in the following. Good. So this is now our left lower quadrant script, left upper quadrant environment, right upper quadrant. And then we have here the plots that are being displayed not only the plots, you also have here packages. So R is providing a lot of packages that you can download while you're basically operating it. And we will discuss various packages down the road, but more of that later. Good. So these are the 4 quadrants of R. So there is more to that, obviously, but that's just a brief overview of what we're looking. Good. One thing that I also want to emphasize, and I have done it here already. So make sure that you have a good folder structure that you set up. And that is obviously for this class, please use a good folder structure and make it just like I did here, that you have here the different folders with distribution tables, fund project, that you have everything organized. I cannot emphasize organization enough. All of you're gonna go into data analytics and data science. I promise you, I guarantee you, organization is gonna be your lifesaver because you're gonna produce thousands of code files, functions, and you will write thousands of lines of code. And I will make reference to how to organize your files, and I will make reference to how to organize your code, because I had to learn this quite painfully myself, and I have seen other analysts, junior analysts, struggling with it. That I have told the same thing. It is relevant that you know exactly where you always find whatever you need to find, and that starts with a folder structure for each project to basically have really these. So these 4 different folders I would recommend. So you start off with a literature folder, and you basically label them with 0, 1, 2, 3, because that way it will keep them always in the same order. And you will use for each project, I recommend you do it that way. For each project, use the same nomenclature, because you will query whatever is in those folders down the road within your code. If you always need to go back, it's like, how did I name that folder? That will be a tedious job to do. If you know it by heart and you right away know how to label and how to call that folder in your code, makes your life easier. So start off, as a recommendation, start off with literature. Then you have 1 is data, because that's the core piece. Within data, I highly also recommend to stratify it into the original import files, and then the files that you have manipulated, that you have worked on, that you have cleaned, and then the temporary files. Makes up folders for everything, and make sure that you have that defined in your code. Then I would recommend to always do a folder which actually contains your code, because you will have codes and functions that you will call from various spots in your code. And then essentially lastly an output file where you will output all your graphs, tables, whatnot that you produce over the course of your project. Also, when it comes to organization within the code, when you write, so I write scientific articles, right? If you write an article and you do an analytic approach to an article that is really analyzed in much detail, you're looking at somewhere between 3,000 to 6,000, 7,000 lines of code. So that's a lot of coding. That's a lot of different files. Organization is key, that you find all these respective bits and pieces again. So I will say it over and over and over, but I cannot emphasize how important it is that you organize yourself. You define at one spot in the code, and you define, you soft code this at one spot in the beginning of your code. And you can always refer to those soft coded variables in the beginning. So something like a file or a folder name, that's a soft code at the very beginning in the first 20 lines of your code. That's your definition. And that is the code which you will refer to in the following over the next 8,000 lines of code. Why is that so important? Because if you would hard code a folder name at each spot in the code where you need it, all the 8,000 files, you're going to have 100 entries of the different folder. And then at one point, you're being forced to change the folder name, then you need to change it 100 times. Right? So from that end, soft coding is really the key to efficiency. So trust me on that one. Good. Okay, folder structure, we talked about that. Any questions on any of this so far? Good. So here we have two codes. Please go on the syllabus, go and download the Open Intro book. Open Intro is a fantastic statistics book. It's free of charge. It's open source. It's still being worked on. Various authors are still actively working on the statistic books. They give you access to data sets, codes, examples, fun examples, really interesting examples that are basically real life data. So you will find all over the internet, you find various examples of data sets that are just really useful and interesting to look at. And you will see this in Open Intro, you will see this in various R packages. Again? Really? No? Out of battery. Okay. Okay. Let's remember the game from last time. Okay. That better? No? Now? No? No? You can't hear anything. Okay. Yeah. We're back. Yeah. Four. Now, does that change anything? No. How about now? Does that do anything? No. Not even a little bit. Okay. Okay. Yeah, yeah. Oh, good. How about now? Now? Okay, I try my very best to speak very loud. I hope that works for now. I apologize. I bring my own set of batteries next time. I hope it's somewhat okay. Okay, so you essentially, and you have the recording, so maybe that helps a bit. Okay, so you basically, where did I stop? I can't believe this. It's every year. Okay. So basically, you have Open Intro is a good resource for you to essentially download data and codes. You have good examples. There is another one that I have posted, which is R for Health Data Sciences. Also there you have data and codes at your disposition that you can look for. It basically accompanies the syllabus of this class. So you have all these different chapters that allow for you to essentially use the same methods that we're discussing in class now. So what this code essentially shows here, we have here on line 1, we're basically querying directly from Open Intro a code that is containing the data from RBUT-NOS. So we're basically just running line 1, and when you run a code, you basically have the possibility to click on Run here, or you can alternatively press Control and Enter. Control and Enter will basically run the line you're currently in. So you can either just click on the line, not select anything, then it will run the entire line. If you start selecting things, you will only run what is being selected in that line, but not anything beyond that. If you want to run the entire code, you basically press Control and A, you select the entire script and you run that all down. And basically, if it's a very intense code with a lot of data, you basically, you do that overnight and you let it run. So always code in a way that each line is chronologically following the next, so that it logically makes sense that you run from the first line to the last line. That you can literally run this as a standalone code, that you can select the entire script, run the entire script, leave the computer overnight, and the next day you come with your morning coffee and your code is ready and your analysis are done. That's kind of the way you should look at this and think about this. Okay, so when we run now line 1 and line 2, we're getting 2 objects now in our environment. One is Arbuthnot, which is 82 observations over 3 variables, and present, which is 63 observations over 3 variables. When you want to look at this data, you essentially would do this. So there are 2 different ways to do that. You can either call this data. Okay, so now I'm in the console. If you press Command and L, Control and L, sorry. If you press Control and L, everything that was written here in the console, whatever you ran from the script, is disappearing. It's easier to give you an overview. If you are running now this and this, it will make these entries here in your console. If you would like in the following to now look at this data, you can address each of these objects in your environment by basically writing Arbuthnot. It will basically run and display the entire object to you. So what you see here basically is you see year, boys, and girls. So this is basically year is the categorical variable. Here you have boys and girls. That's the accompanying discrete variable, right? So it's the count of boys that were born and girls that were born during these years. So the same will be true for present. It's the same data layout. It looks the same way. So you essentially have now these 2 variables. You can also open them. And this is basically where RStudio is very user-friendly to you. So if you go here at that object, you have here on the very right something that looks a bit like a spreadsheet. And if you click on that, you basically have here year, boys, girls, basically presented like an Excel spreadsheet. But you can't really compute in it like in Excel. You need to do this programmatically in your console. But you can look at it, which is, to be honest, only something that you can do with small data sets like that one. If you have a large data set with like 100,000 of patients, it's like you open this that way, this is going to take you half an hour until it's open. So you don't want to do that. You really want to think of this. How can I approach it programmatically rather than visually depicting it there? Next, on line 4, we are creating an object that is called write folder. What does write folder contain? Write folder contains the file location where you want to go. And you remember output was the output folder where we want to output data to. You basically get through that folder by, it's actually 3 output. You can reproduce this folder by clicking on output, making a right click. So if you click on this, you make a right click. No. So on a Mac, you make a right click on the folder, and you see here copy. So that is copying a folder. You don't want to do that. You want to press Option here. And when you press Option, you basically have copy 3 output as path name. And that's really what you want to do. Those of you on a Windows computer, you need to right click, go on properties and copy that folder into R. The only thing, so if I copy this from Mac, that's quite simple. And that basically gets me now exactly what I need here to have output, to have that output folder defined, right? What you have to be careful with a Windows computer, Windows uses a backslash to separate folders from each other. You need to replace those backslashes with slashes because R uses a different underlying coding language. It uses slash, not backslashes. So you need to change that. Good, but we have now this folder created and we can now have now this entered as this write folder. Why do we need this write folder? Because here in the following, after we did our summarization, we want to do PDF outputs. And those PDF outputs will essentially use that write folder to utilize this as the destination of our PDF file. And the outcome of this practice lab for today's class will be to get to that level that you have those PDF files. So that will be what you submit to me. That's the PDF. But we'll get there. Okay, so first of all, if you start an entire object, it will give you the entire object. It will display the entire object. Sometimes you don't want to see the entire object. One way to display only part of this object is by writing head. Head only gives you the head of Arbuthnot, which is basically only the first 6 entries. It can be more than 6 entries. You can be head 10, gives you 10 entries. So it's basically, this is the way how to have a quick look at your data and see how it presents to you. You can see the different variables and you see the first 6 entries. You kind of get an idea of what's contained without having to open it. If you do ls, gives you a list of variables included in that object. I hope I'm loud enough. I apologize for the technical issue. I really give my best to be loud enough. So if you do ls Arbuthnot, you basically get all the variables listed here that are contained in your object. Each of these variables can be explicitly be addressed with the $sign. If you have Arbuthnot $year, it will only present to you and will display the respective years that have been recorded. You can do the same with girls, then it only gives you the count for girls, and boys gives you the count for boys and girls. You can use this to do calculations on that. So you can hypothetically, you can go and summarize them. Well, let's go further. You can calculate the ratio between boys and girls. So that's here on line 26, for example. You have Arbuthnot ratio. That's the ratio between boys and girls. So it's boys over girls. And just calculates a ratio between the counts. So you can online essentially create new variables using arithmetics on the entire variable in your data set. And that is true even if you have 100,000 of entries, you can do the same computations. You can do subsets of that. So this is, so line 26 does this ratio, which admittedly is not as insightful and doesn't help much, but basically you can do computations. So that's what I wanted to show you with this exercise. If you go back, you can hear Arbuthnot and the brackets here can essentially give you a way of subsetting this data. So if you're interested in finding the year with the maximum number of girls born in the UK in the 17th century, you can do this with max Arbuthnot girls. That gives you the maximal value. So that's the maximal value of girls that were ever born in during that time. If you want to have the girls entry, which was max, you basically can run line 14, gives you that entry of that year and the number of boys and girls and the ratio for that particular year. So you follow along a logic by saying, okay, so I want arbuthnot with the bracket, you're defining what you want to show, what you want to address. You're saying we're arbuthnot girls. So this indicates that entry of that vector, of that variable, where the value of girls is actually consistent with the maximum entry of girls. So now there are a million different ways how you can do that, but I am showing you this because this is one way how you can define exactly what it's looking for. So it's kind of my way of explaining to you how you can address specific entries within a data set with R. Good. So now you have, you can do the same with min. So you have here the max that was in 1705. That's where most girls were born. And then in 1650, there were the least amount of girls born over the observation period of 55 years. So you can do the same analysis here with boys. That's not really that relevant, but you can also calculate proportions. You have ratios and you have proportions. So you have proportions, you're basically calculating boys over all the children, where you quantify the children as the sum of boys and girls. So that's line 21. So now once you have the children, you can calculate the proportion by dividing the boys by the children. That's a proportion that basically gives you here a proportion of a mean of 52%. Proportions multiplied by 100 gives you percentages, and that is essentially how you get further. So these are simple codes, how you can address the specific entries in that data. And you can do these computations and you can play around a bit with them in the following week at your disposition. So when you have a PDF, the PDF function basically allows you to export a PDF file, a PDF graph. And the code is considerably simple. So you basically use the paste function. So paste is essentially a function that allows for you to put together different things that you concatenate then, and you can use, you can basically put them together in a way that it will remove all separating factors. So IM5002. And with a separator, quotation mark, you're basically removing separator equals quotation mark. You're basically removing everything in between. It's not good, missing a bracket. So you're basically with paste, you're pasting and concatenating various things together and you're expressing it as one. So this, for example, would show exactly that. If you take paste, right folder, and practice lab 1.pdf, it would basically give you exactly, it would give you this, which basically is our right folder, and then the file name attached to that. So it basically concatenates the right folder and the file name together, incorporates that automatically in the PDF function, and will now take the graphs in the following, added here into a curly bracket into the PDF. Up until the end where the curly bracket is closing, finally closing, and is followed by device.off, which basically tells that our plot engine that now to shut down and conclude and complete that PDF of that graph. So if you go and run that entire thing, you basically see at the end device off. You have null device. Make sure that this is entirely closed. Sometimes you need to rerun it, but you don't need to. But you basically, you go now in your output folder and you have here PDF. So that's essentially how you would create a PDF in R. So it's really as simple as could be. So it's essentially the overview of these birth numbers over time, over the entire observation period, that basically shows that R was not data. For practice lab 1, the deliverable is essentially to send that graph and to also do the same exercise for the present data file. That to me as practice lab 1. Good. So I apologize for the technical glitch. I hope you were somewhat able to understand me. I'm gonna speak outside with Ariana to get batteries for next time. I hope it was fine. You do have the recording. The entire lecture was recorded. So you can go through the coding steps again, step by step. If you have any questions, on Canvas, there is a discussion board. Utilize the discussion board, poke me and tell me that you have posted something on the discussion board, and we can have a conversation as a class on the discussion board. So these kind of classes, there's a lot of coding and coding questions that will come up. It's just nice that everybody can contribute and can listen in on the conversation in case there are any debugging or coding issues or whatnot. I really want to make this an interactive kind of class. And it would be great if you would post your thoughts and whatnot on the discussion board to essentially facilitate the conversation. Good. Any questions? If not, have a nice evening, and I'll see you next week, Tuesday.